Welcome to this video about the A-level physics required practical into stationary waves or standing waves. In this practical, you're likely to be asked to investigate how the fundamental frequency of a stationary wave varies with either tension in the string, the length of the string, or its mass per unit length, and you should be prepared for exam questions on any of those variables. Just to do a quick recap on what stationary waves are. So stationary wave is formed when you have two waves traveling in the opposite direction that can interfere or superposition can occur, and they form these shapes with different loops on them. If there's just one loop visible, that is known as the fundamental frequency or the first harmonic. If there are two loops, it's the second, or three loops, it's the third harmonic. It's the second harmonic that contains one full wavelength because the wave goes up to its peak, down to its trough, and back to the equilibrium point. So that'll be one full wavelength, meaning that the fundamental frequency or the first harmonic contains half a wavelength. So if I was to make L the length of the whole wave, then 2L would be one whole wavelength for the fundamental frequency. The equation to calculate the fundamental frequency of a stationary wave is given by F equals 1 over 2L times by square root of the tension divided by the mass per unit length. You don't need to know where this equation comes from, but it's helpful to look at what it means. So when we look at frequency and wavelength, we should know they're inversely proportional. And as we said earlier, for the fundamental frequency, 2L is equal to the wavelength. So we could express this as F equals 1 over the wavelength times by root T over mu. So in this case, if we rearrange a little bit, we have wavelength times by frequency on the left-hand side. And from our wave equation, we should know that frequency times wavelength equals speed. So if the left-hand side equals speed, then the right-hand side equals speed as well. So in this practical, you're likely to be asked to calculate a value for speed by varying the length, for example, and then compare it to the value by doing the square root of the tension divided by the mass per unit length. So let's have a look at the experimental setup. You'll have a signal generator, which generates the signal at a specific frequency. You'll have a vibration generator, which transfers that signal in vibration form to a piece of string. And then you have, over the other side of the bench, a movable bridge, which you can change the length of the string that's experiencing the wave using. And then you have it draped over a pulley with some masses at the other end. So the tension here is provided by the masses. Tension is a force, and the force that's going downwards is weight mg, T is tension pointing upwards. L is the distance between the vibration generator, where the string starts, and the movable bridge. And the signal generator will have a frequency on it, which indicates how many times per second the wave is travelling from left to right. The method for this practical will vary depending on what variable you've been asked to change and what you're trying to calculate. But method 1 here, we're going to look at how the frequency or fundamental frequency varies with the length if you move the movable bridge. So the method for this version of the practical will be to adjust L, the length, using the movable bridge to, let's say, an initial length of 1 meter. Then you have to adjust the frequency on the signal generator until you see the pattern seen here, which is going to be the one loop fundamental frequency. You have to find exactly the right frequency, otherwise you won't see that shape. Then you record that value of the frequency, and then you reduce L by, let's say, 10 centimeters each time. You obtain roughly 8 readings. The idea is you take enough readings so that you can do repeats, find a mean, and you're going to plot a graph. Before you do that, you need to record the tension by using tension force equals mg, where m is the mass in kilograms. And the mass per unit length is just a value of the mass of the string divided by its length. So if you have 2 meters of it, for example, you measure the mass of it on some scales and you divide by 2 in meters. An alternative to stage 3 is instead of relying on the signal generator to tell you the frequency, you could be asked to use an oscilloscope to find the time period. So to find the time period first, oscilloscope, you need to measure the distance from one peak to another on the oscilloscope, and then using the time-based setting on the oscilloscope to find the time period. Then the frequency is just 1 divided by that to give you the frequency. It is generally more accurate than trusting the signal generator, but you should find they're relatively similar. So let's look at the analysis for this practical. Let's say you've got a bunch of readings for different lengths and their fundamental frequency. Using the equation as we looked at earlier for fundamental frequency, we can see that if tension and mass per unit length are constant, as they are here, then the frequency is going to be inversely proportional to the length. So if we plot a graph, instead of just doing frequency and length and finding out it's inversely proportional, we're going to use the gradient in this practical. So we're going to plot on our axes f on the y-axis and 1 over L on the x-axis to prove these two things are proportional. Then we can use the gradient to find something out. So for this practical, the gradient is going to equal y over x is going to equal f over 1 over L, which rearranged gives you f times L. As we talked about earlier, the wavelength of this wave is equal to 2 times L, and the speed is equal to the frequency times by the wavelength. So therefore, if the gradient is equal to FL, then to find the speed, we just need to multiply that by 2, because it's got to be F times 2L. So the speed can be found by doing 2 times by the gradient. Then we compare it to the measured values we looked at earlier. So square root of the tension divided by the mass per unit length. Those values should be within a certain percentage of each other. Calculate the percentage difference, see how close they were, and we'll talk about the uncertainties a little bit later. Let's look at the second version of this method, where instead of looking at frequency and length, we're going to look at how fundamental frequency is affected by the tension. So what we're going to do here is adjust the tension by adding masses each time to the hanger and record tension each time for each value of mg. The second step is the same. We need to adjust the frequency on the signal generator to when we see the first harmonic appear, and we're going to record F and then increase the tension by adding 100 grams or 0.1 kilograms each time to attain at least 8 readings to plot a graph. Then this time, the things that are constant are the length and the mass per unit length. So we're going to measure those just to make sure we know what they are so we can compare the values measured later. So from this equation, hopefully you can see that frequency is not proportional, not directly proportional to the tension. But if I was to expand out our square root and square everything, I'd find that F squared is equal to 1 over 4L squared times by the tension over mass per unit length, meaning that the overall relationship is that F squared is proportional to T, because everything else in that equation is constant, the way we're doing this practical, including length this time. So what we then plot on our axes are F squared and T, and we see if they're directly proportional or not. It should be a nice straight line, and we can use the gradient to calculate something similar to what we did with the length version of the practical. It's worth noting here that when you're doing this practical, you need a bit of a bigger table, because this time you're measuring the mass, but then you've also got to calculate the tension in a column to plot on your graph, and you're also not doing F and F squared, F by itself, you're doing F squared. So you might find you need an extra column to do those calculations. It's good practice not to do it just on the graph, you've got to put in the table as well. So for this graph, the gradient is equal to F squared over T, which if we rearrange our equation for, F squared over T is equal to 1 over 4L squared times by the mass per unit length. So this time, if we wanted to do the mass per unit length calculation, we'd switch places with the F squared over T, and we'd find that mass per unit length is equal to 1 divided by 4L squared times by the gradient, or F squared over T. And with this practical, you could then compare the value you've just calculated from your graph to the measured value, so the actual mass of the piece of string divided by its length. Again, see how close they are, calculate a percentage difference. So let's talk about the uncertainties you could be asked to calculate in this practical. If you don't know how to calculate uncertainties or what the general principles are, I'd recommend watching this video first on uncertainties. So to calculate the percentage uncertainty in the frequency, we first need to work out the percentage uncertainty in t, the time period, if you've measured it on the oscilloscope. So therefore, in that case, we'd do the resolution, so the number of seconds per division on the oscilloscope, divided by the actual value of t. Then the percentage uncertainty in f would just be equal to that, because it's just f equals 1 over t. Just use them in the same way as a percentage uncertainty. The percentage uncertainty in L would just be its resolution, so likely to be 1 millimeter in your ruler, divided by your value for L. When you're working out the uncertainty in a gradient, it's a little bit trickier. Once you've got the percentage uncertainty values in F, you can then add them onto your graph and make some error bars. Once you've got that, you can then compare your gradient with the line of best fit with a line of worst fit, or LOWF here. And the percentage uncertainty in a gradient is going to be the difference between those values divided by the line of best fit gradient, and then times 100 to make it a percentage. You could use either line of worst fit, the steepest or the shallowest, but either way it has to go through the error bars to make it a line of worst fit. Let's have a look at common errors in this practical, or errors that can occur. So the main one is a sort of practical physical one, which is determining the exact frequency at which the first harmonic occurs. Because sometimes it could be kind of hard to see exactly where that frequency is, because the wire is always vibrating. How do you know exactly where it's the highest? So you need to make sure you do this at eye level with the wave, and you could place a ruler behind it to find when it's at its maximum amplitude, so it's easy to see, but make sure you're measuring it from the same position each time to avoid parallax error. You want to make sure you have repeats for this experiment and find a mean to reduce the impact of random errors. And as we mentioned earlier, using an oscilloscope to calculate F independently is going to rule out any issues with the signal generator not being exactly the frequency that's coming out via the vibration generator. To measure the length of the string, usually the meter ruler won't be exactly level with the string because it's in the air, so you could use set squares or something to make sure you're measuring exactly from the end of where the string is. For safety, you want to make sure you clamp the whole thing in place, especially the vibration generator or the string, for example, and you want to make sure no one's standing at near the bottom of the string where the masses are, so masses don't fall on people's feet. So there we go, that's the stationary wave required practical. Comment below if you want me to go through a specific required practical, and please leave a like if you found it helpful. Thanks for watching.